Okay, can I start?
Yes, please.
Yes.
Yeah. Okay. Good afternoon and good evening to everyone. We continue with the photovoltaic and introduction. So the third part, solar cell for energy solution. And today we're going to talk about the p-n junction and the light absorption and the photovoltaic effect. So the first part of the talk, we talk about the p-n junction. We're gonna see how it looked like the drift field driven current. So basically, we talked something about that in the last lecture, and I'll just gonna remind you about that. Then we're gonna talk about diffusion current, which we basically have because of concentration gradient when we have a p-n junction and a different concentration on the hole and electrons. Then we see how it looked like basically when we form the p-n junction, and we talk about the built-in voltage and the field, and also the space charge region or depletion zone or depletion region, how we call this. Then we talk about the current contributions, different current contributions, and we're gonna see how it looked like if no applied voltage we have. So if we don't have a voltage, and we also see how it looked like when we have a forward bias junction. And we end up in this part with the ideal diode equation. After that, we're going to talk about the light absorption and the photovoltaic effect, and finally see how the solar cell is working. Then we're gonna, in that part, we talk about the linear absorption coefficient and the band gap, and we're gonna see how the linear absorption coefficient oscillate a lot around the exactly value of the band gap. Then we talk about the creation of photo-generated carriers and their energy, and then we see what is the difference between the direct and indirect band gap, because the solar cell can be made then from the direct and from the indirect band gap. Then we're going to end up with the equation for the solar photocurrent, and then we said something about the current convention in solar cell, and then we end up with the solar cell current voltage behavior, and the most two important point in this curve, that's an open circuit voltage and the closed circuit current, and we finish with equation for voltage and for current, and these are two important part of the current voltage behavior which we use in a calculation of the solar cell efficiency. So basically, now we can start with the drift current in semiconductors. And we said something about that when we talk about the current density in semiconductor in the last lecture. And we said basically that the drift current is just the voltage driven motion of the charge carrier. So we have here some chunk of semiconductors, and basically built from the holes and from electrons, and then we're going to apply some voltage here. So basically dependence on the voltage in the position will be negative curve. So here the voltage will be higher than downstairs, and then in this point, and then basically that we have applied electric field will be going from this direction to this direction, and then basically the electric field will be just the negative gradient of the voltage, and this is the negative derivative of the voltage, and we end up basically with a drop in voltage divided by the length of this material. And here you can see basically that the applied electric field is constant and basically the positive. And when we have a charged particles, we also have a force on the charged particles due to applied electric field. And this force is just equal to the charge times electric field. And for instance, for the holes where we have a basically positive charge, basically that force to the right we can write down as a drift velocity. We have that, and we explained this in the first lecture of this introduction to photovoltaics. I'll just remind you here that the drift velocity, this is for the holes is basically proportional or equal to the mobility of the holes times electric field. And for electrons, where you have a basically negatively charged, then you have a force to the left. Here you see going to the right and electrons going to the left. And then we have that the drift field of the electron is just the negative, basically sign mobility of electron times electric field. Generally, the both charges contribute to the same sign of the current. Gonna see here, because if we remind also something that we said about the Ohm's law, that basically this is also something from the first lecture, that the current density we can write as the conductivity times electric field, or we can write down as the number of density times charge times drift velocity. And here we're gonna see that for the holes, this current density will be basically the number density of holes times charge times drift velocity, and then drift velocity we'll see that we can write down as a mobility times electric field. So basically it will have a positive sign. So the holes drift to the right, and we call this positive current. So now for electrons, we're gonna have basically the same equation. Just now we're gonna have a number density of the electrons, and then we have a negative sign of electrons, and then we also have a negative sign for the drift velocity of electrons, and that's basically this expression will be positive. So basically when we said electrons drift to the left, it will give a positive sign, because when the electrons going to the left plus have a negative sign, that's it will be basically the positive current. And then the total drift or the field induced current will be just given by this equation. So just basically for the holes and for electrons. And here you can say that depends on the mobility and on the electric field. Just to remind you something which we are saying for the mobility, and which can be interesting here. In general, mobility is a function of the temperature and also the doping. And here we give something, some value of the mobility of electrons and the holes for different semiconductors, silicon, gadolinium arsenide, and germanium. Usually mobility, that's mobility are given on the 300 Kelvin and for low concentration doping. Usually the mobility of electrons are much higher because of the lower effective masses of electrons than the holes. When we remind ourselves what is the drift field and current, basically then we can go in the new part story, and that's diffusion current. But before basically we show how it looked like the equation for diffusion current. We said in the beginning something generally about the diffusion. So basically we said that the random motion results in a flow down the concentration gradient. And basically the flux we defined of how many of given species pass by per area per time. And basically they are measured by the number per area per time. And also this flux is related to the current density. Current density is also known as the current flux. Okay, and it's measured by the charge per area per the time, and because the charge per time is just to represent the current, that is basically the current per area. And the current density is just the flux of the charge carrier times their charge. And the symbol that we're going to use for flux is just a G. And now when we talk about, we're going to say something about the atom concentration. When I said here, when I'm talking about the diffusion, I'll basically talk here about the atoms or some kind of species, but basically the same things I'm saying, they will also apply and for the electrons and holes. That's why we basically talk about the diffusion because and concentration gradient, because we'll see that you're going to have a concentration gradient and diffusion when we talk about the p-n junction. And here we can say that basically atoms per volume for some position, basically Z can be expressed as atoms per area and divided by basically the plane spacing. And now to just explain what the flux is, if we look something like some crystal lattice or some matter, and let's we say that here we have some imaginary plane, and let's say that we have here the dark species or the atoms, which they are completely here next to this imaginary plane. And after that, we allowed this dark atom basically to moving around everywhere in this basically lattice, and that movement of the different atoms basically, and crossing this imaginary plane will be nothing else than the flux. That's why we flux define as a given species passing by per area and per time. And of course, when we said basically that we have imaginary plane, that we said also that the some atoms will shift to the right and some atoms will shift to the left side. And that's how we can define basically the flux to the right and also flux to the left. And just flux to the right is just or the positive flux, how we call them, because also the holes moving to the right, so they are positive, can be basically expressed as a 1/6. 1/6 is basically because the atom can have one of the the direction in the cubic lattice. When you let this atom to rearrange, they can go up, down, they can go left, right, they can go according to diagonal and everything else. And then we have basically the atom hopping rate here in expression for the flux. That is just the atoms which they move or they hop on the different position and different direction. And here we have basically atom per area. And here on the right side, we have an expression for the flux to the left side, and flux to the left side or the negative direction of the flux. It will be basically the same expression, just now we're gonna have here Z plus delta Z. And that's the net flux from the two planes of atoms crossing an imaginary plane between them. Because if we take this, if this is imaginary atoms, then if we take these two planes, so these atoms basically can move across this imaginary plane, and then this distance between two planes imaginary will be basically delta Z. So that the net atoms of a species of flux can be just expressed by G plus minus G minus, and we can use this equation here, and basically atoms per area can also express in a function of the concentration, atoms per volume or the concentration, and the distance between the plane. And if we take basically that this distance or delta Z is quite small, then we can instead of delta write the differential can be expressed as a derivative. I'm sorry. And here we have a derivative of concentration and depending on the position. And here basically the hopping rate and the distance between the atoms will be represented by diffusivity or diffusion constant. And here we're going to have a concentration gradient. So the flux is proportional to the derivative concentration with position. And this law is quite well famous as a fixed first law. And now we can, this is also the same equation, just here expressed for GA. First flux, and this is diffusivity or diffusion coefficient. And basically, we said that the random motion results in a flow from the regions high concentration to regions of the low concentration. So if you look the concentration depending on the position, so we're gonna have a basically shift of concentration from the place where the concentration is high down to the place where the concentration basically is low. And then we said that the diffusive flux flow down the concentration gradient. So that will be also the way of the flux. So of the flux. And here we're going to see how it looked like now, the diffusion current in semiconductors. So here, basically, here is for electrons depending on the position, and here red line is just the concentration. And here, basically, we can see that, that this curve is going from the higher concentration to the lower concentration, and that's also meaning that electron flux is going direction. And if we express this now, diffusion current for electrons, it will be basically this diffusion part, which is negative here, diffusion constant and concentration gradient, time negative charge. So basically, we're going to get the positive sign of diffusion current for electron. That's why electron have this direction. So for the holes, here we also have basically concentration gradient, so the holes are moving from the place of higher concentration to the place of lower concentration, and the hole flux we're gonna have also this direction. And if we express how it looked like diffusion current for holes, then we basically, this is the positive charge, but the flux basically have a negative sign. So basically, the diffusion current for holes will be negative. So that means that the hole diffusion current density will have an opposite way than the electron diffusion current. And because we remind ourselves that the total drift field induced current in their description have basically mobility, it would be nice that we now diffusivity or diffusion constant also related to mobility. And we can do this by using the Einstein relation, where diffusion coefficient is just related to the mobility. These are just the constant, Boltzmann constant and the temperature. So basically, the total current have two components, and that's the drift current from electrons, and here is the diffusion current from electrons. Part is connected only for electrons. And here we're going to have a part concerning the holes, and also will be built from the two parts, drift current from the hole, and also diffusion current connected with the holes. And now we can see what is happening basically when we connected the N-type material together with the P-type material. But before we discuss this picture, we just remind ourselves from the previous one and from the doping. So we said if we have an N-type doping, that the conduction band is full of electrons, and then the chemical potential or the Fermi level basically shifts due to the doping close to the bottom of the conduction band. And if this concentration of the electrons are higher, then the chemical potential will be closer to the bottom of the conduction band. And for the P-type dopant, basically is opposite. We have a valence band which is full, and chemical potential shifted to the top of the valence band. And if we have a more concentration of hole, more will be chemical potential close to the valence band. And now we're going to see what will happen. Basically, we connect it together N-type of semiconductor with a P-type of semiconductors. So we said that one of the first things we're gonna explain that's basically diffusion. So the electrons from N-type region, because of concentration gradient, just will shift from the N-type region to the P-type region, and also hole will shift from the P-type region to the from the N-type region. And when the electrons shift from the N-type region to the P-type region, he will gonna left the positive ion course here. And when the hole's moving from the p-type region to the n-type region, he will basically left the negative ion cores. This basically this part is completely full of the positive ion cores, and this part here is completely full of negative ion cores. And basically, these charges are fixed; they are not moving. And this part basically we call the space charge region, and because it's depleted by the positive and the negative charge, we also call and depletion zone or depletion region. I call the depletion zone. And because basically we have the fixed charge here from the one and from the other side, positive and negative, we can say that basically we built an electric field. So we can generally summarize the diffusion result in a charge regions due to the fixed charge of the doping ions. Charge regions result in an electric field. An electric field produces force that opposes the further diffusion. And now, basically, when the electric field is built, now he will oppose diffusion. So now the quite a large number, for instance, from the n-type region, electrons, which they move into the p-type region, now will going because of the built electric field. Now he want to coming back basically to this positive to the back, and also the holes which they moving to the n-type region because of the built electric field, they will basically wanted to return now in this in the opposite direction. So that's why we basically said that diffusion flux of electrons, which we have because of concentration gradient, and we have a diffusion flux of the holes because of concentration gradient, will basically the opposite the electric field, which is built electric field flux of electrons, which now will move returning electrons in the opposite direction, and we're gonna build also the electric field flux of the, which will now trying to return in also in opposite direction. And on the next slide, basically, we're gonna see that now we have completely the same picture, n-type, p-type, space charge region or depletion zone. And basically, we're going to say that eventually diffusion and the drift flux will balance. And as the circumstances of this balance, basically the chemical potential will be the same through the junction. And if you represent here the N, the PN junction or the NP junction here, so basically we're gonna see that the chemical potential to the junction will be completely constant. So this is this line here, and this is just the chemical potential for intrinsic semiconductors. And because basically now we're gonna see that for instance for n-type region, in the n-type region, so the bottom of the conduction band, which is close to the Fermi level, and in the n-type region, now we're gonna shift through this junction in the p-type region, where it's basically far away from the chemical potential. And this gonna be also for the holes. Now in the p-type region for the holes, top of the valence band, which is basically close to the chemical potential, it will now shift because of built-in voltage down to the n-type region, where it's basically far away from the chemical potential through the junction. This dotted line here. And now we can say basically that we're gonna have here band edges are basically potential offset. So now we're gonna have some difference here between the real between the chemical potential in the PN junction and also intrinsic chemical potential, and in n-type region, and also will be some difference here in p-type region. And now we try to calculate this potential offset, and this calculation basically we need, because when we calculate this, then we can find the built-in voltage, which is formed basically due to this phase charge. Now we can see how we can calculate this. So if you basically look how it's look like this potential offset, now you can see basically that this potential offset in N and P-type region will be basically the same as the difference between the real chemical potential in the p-n junction and intrinsic basically chemical potential. And we're going to calculate this. We remind ourselves for some equation from the first lecture, when we basically express here electron density in n-type region by this equation, where this representative effective conduction band density of state. Here you have exponent, and here you have a basically bottom of the conduction band and the chemical potential. And we said, just to remind you, when you have a really doped sample, then your chemical potential is really close to the bottom of the conduction band, and then this one part became a small, and then you have a negative exponent, and then your electron density basically grow. And then we're going to use the next equation, which is intrinsic electron in n-type, which will be completely the same. Just now we're going to use basically intrinsic chemical potential here. And if we take basically the ratio of electron density in n-type region and intrinsic electron in n-type region, then we're going to get here in exponent exactly the difference between the real chemical potential and intrinsic chemical potential. And that's something that we'll need to calculate the potential offset in n-type region. And from this equation, basically you can get the potential offset, which depends, which is the function. Okay, these are the just constant, Boltzmann constant, and the temperature. And here you have number density of the donors. Of course, if all donors are iodized, we said that in the last lecture, then far away here in the n-type region, number density of donors will be basically the same as number density of electrons. Do completely the same calculation now for the potential offset of the p-type region, and now you're gonna have for hole density in p-type region, we're gonna have completely the same basically expression. Just now here NV will be effective valence band density of state. And here also we can also express here intrinsic hole density in p-type region, and then we can find basically this difference and then express potential offset in the here in the p-type region. And then we also, of course, end up with the equation, which depends on the number density of acceptor, and if we are far away here in a p-type region, and if the all acceptors are ionized, basically this number density of acceptors will be number density of we are equal to the number density of the hole. And now when we have basically the potential offset in the n-type region here and the potential offset in the p-type region here, then we can calculate what is the total built-in voltage. And the total built-in voltage will be the sum of the potential offset in the n-type region and in the p-type region. And that voltage that we get, basically that's the voltage that we get for the solar cell, and which is quite important for us. And we need to know this equation, because after that we're gonna see how this built-in voltage basically will change when we applied voltage. For now, we don't have a voltage for now. And here we can see, we can also see that this built-in voltage also depends on the doping. Here, the next one is just schematically represent what we are having so far, because this is current contributions at equilibrium. So far we don't have any kind of applied voltage here, but sometimes it will be quite easier to understand what is happened with the minority and majority of carriers if we schematic presentation when we apply basically a voltage. And here we have basically and its equilibrium. We said that both electrons and holes have a diffusion flux or concentration gradient flux, and we also have a drift field flux. And the total flux is, of course, can be represented of the from the part of the drift field flux and diffusion flux, of course, and for the electrons and for the holes. We have here the drift field, and we also have here the concentration gradient of the flux. And here, for instance, we can draw this quite easy. So this is just a real chemical potential in the p-n junction, which we said is constant when we don't have applied voltage. You're gonna see that it change when we applied voltage. This is just basically the bottom of the conduction band here, and in p-type region we have basically the minority of electron carrier here in the conduction band. Of course, the highest number of this minority electron present here in the n-type region will be basically the highest at the lowest energy level, and then that number basically decreasing how we go up and how the energy of different electronic level increases. And on opposite side, in n-type region, electrons basically represent the majority of the electron. And here you can basically see that here is also the same story. So the highest number of the electron here will be basically close to the bottom of the conduction band, or will be situated in the lowest energy level, and then how we go up and the energy of the electronic level going increasing. If we going up, then we'll basically decrease the number of electrons. It will be completely the same story. And for the holes in n-type region, you have minority of the holes, and just here for the holes it will be opposite, because the here the energy level of the hole here is the smallest, and then the energy of the holes increases how we going down. And here, of course, in the p-type region, the holes are majority species in this type region. And now we can basically set, so what is happening? Now this in a p-type region, minority electrons will basically shift due to the drift flux here. But here, certain number of the electrons from majority of electrons, which they are high enough in this band, will be drawn to this space charge region due to the flux gradient in all direction. Basically, here we said that the electron drift flux is basically the electron diffusion flux, and the current through the junction must cancel for each carrier type. Same story will be absolutely for the holes. So here, the minority of the holes will be also by hole drift flux on this way, and this one, majority of the holes, they are high enough in the band, so some of them will be basically will be going in the opposite direction due to the hole drift flux or concentration gradient. And this is if we have applied. And now, basically, to now further, we try to calculate and how big is this thickness of space charge region or depletion zone. This is quite important because it will be much easier to follow what is happening with the charged species when we apply basically electric field. And now, for instance, if we look how it looked like, the charge density, here we just, in this depletion zone, we just give some coordinates. So if this point is basically 0, when this positive and negative charge are connected, then basically the end of this depletion zone will be basically negative, and it will be the coordinate -6n, and in opposite direction, basically end of this depletion zone will be coordinate xp. So, for instance, so we can basically charge distribution, we can define by this condition where the for the basically the where for the positive ion course basically will be from x will be from -6n to the 0, and for the basically for the negative ion course, it will be x from the 0 to the x. And now the just charge density can be represented here. So for the positive species, up, and for the negative species, it will basically go down. And now to calculate the electric field, what is happening with electric field, we can use the Poisson equation. And the Poisson equation and electric field we can find just by integration of the ratio between charge density that we already defined and the electric constant. These are just mathematical basic conditions for this calculation of electric field, and this is also mathematical expression for this function we get for the electric field, or opposite. If we integrate this part of the curve of the charge density here, then for electric field we're going to get this line up, and if we integrate this one part down for the negative charge, then we're going to get a line which is going down. And for calculation of the thickness of the depletion zone, we also going to use charge conservation, where they basically said that this one thickness of the xn times the number density of the dome must be basically equal to the this one position here of the depletion zone times the number density of the acceptor zones. And now we're gonna see how. So if we recall basically that the electric field, it's negative derivative of the voltage for some position. So then the voltage drop, will be interesting basically to find here. It will be and the voltage drop basically it will be the highest here in the space charge region or depletion zone. We just integrate from this point -6n to the xp. Here you can see the integral, and from the electric charge. So basically, and this is something which you can get for electric potential here. So basically it's changing by getting integration of this surface here, and here you're gonna get this one value here. It's basically built-in voltage, and here we can see that we can express by the thickness of the xn and also the xp, and then we just easily can solve by the xp and xn, and finally, as assumed, we can find white of the distribution zone or the space charge region. And as you can see, this white here will depend on the built-in voltage, and of course will depend on the concentration or the number density of acceptor ions and also the donor ions. And now we're going to see what is happening if we apply the voltage here. So basically, here we have a voltage, and now basically the applied electric field, we're going from here, from p-type and coming across this space charge region, and from the n-type, and this direction basically of the current from the P-type to the N-type region, we call forward bias junction. And the applied voltage drop will occur across the space charge region. There are no carriers there. And this is because basically here in a P-type region, so you have you're gonna have a hole, and here in an N-type region, you're gonna have electrons, and their conductivity will be much higher than in this space charge region where you have a negative ion cores and also positive ion cores, which they are fixed. So the basically drop of the voltage will be the highest here in the depletion zone. And if we basically apply this voltage, then we're gonna get the expression that we get when we don't have a voltage. We have only built-in voltage, and now we're gonna have built-in voltage minus applied voltage. And of course, the rest of the equation will be the same. So that's mean basically we applied here the voltage junction wide, it will be the. So now here, we have from the disposition where we don't have applied voltage, we're gonna shrink in this position here. So for the positive ion core, and here also without applied voltage here, they will basically shrink to this direction when we applied voltage. And also the maximum field will also, now we are integrate the smaller basically surface here, so this one maximum shift will also shifted here. So this one lighter line is connected with the electric field without applied voltage, and this will be after applied voltage. And also electrical potential will be increasing. Dotted line is just the built-in voltage, and now we're gonna get, of course, the difference between built-in voltage and applied voltage. Now we're gonna see what that means in our case when we apply voltage. Are we going to get a higher current? And here, basically, the first picture is completely the same picture as I already explained you when we don't have any kind of voltage. But if we apply voltage, then your chemical potential, which is completely constant here through the junction, now is basically change here, and for the p-type region and for the n-type region. So basically for this charge time the applied voltage. And now basically we can see bottom of the conduction band is shifted up. This one difference here is smaller for the applied basically voltage than this one difference here where there is no applied. So basically how this will gonna change this story. It changed. So here in p-type region we said that we have a minority of the electrons, and this and the story for this minority of the electrons, it will not be changed. But here when we shifted basically the bottom of the conduction band, so now we have a much higher number of the electrons above this band that we can use basically current. So for the concentration gradient. So now this one contribution of the diffusion current, which diffuses to the junction in the p-type region, will be much higher than the contribution from the basically from the minority species of electrons here in the p-type region, which will be moved thanks to the drift field induced current. And that's also means that the more, we already said that the more majority carriers diffuse to the junction, an increased minority carriers right at the junction. And that's basically means that because now much higher number of electrons N-type region to the junction to this P-type region. That means that many of the electrons now, which are in excess, will be basically situated here next to this depletion zone, depletion region. And some of them, of course, because now you're going to have here in a P-type region, when so many electrons come here in a P-type region, there will be no more equilibrium. So some of the electrons, which they came here basically in a P-type region, will recombine with electrons. Everybody knows when the electrons recombine with the holes here, but anyway, current they represent will persist here. And for the to get basically the ideal diode equation, we're gonna calculate how much is current which they persist because we have a now shiftment on the much higher number of electrons of N-type region to the P-type region. So completely, basically the same will be the story and for the quarks. So now this diffusion of the quarks, the basically the diffusion current part, because the higher concentration of the coal will participate in here will be higher than the basically the drift current over here where the coal side minority species direction. And here we also gonna have in this part basically concentration of the coal, majority of the coal. So here somewhere we're gonna have something like a concentration gradient next to the depletion. So basically, if we apply the positive voltage forward bias current, your current basically will.
Hey, Ivana.
But now we're gonna see what is happening. Huh?
Yeah. For a moment, like for a few moments, the sound wasn't, we hear you, but it's kind of interrupting. So I don't know if you want to get closer to your computer or something like that.
Okay. I'm sorry. I'm sorry. Okay. Do I have to repeat something?
I don't think so, unless others want to do it.
Okay. Nothing. Before we go to the basically ideal diode equation, we just going to check what is happen if we have a reversed bias current. So in the reverse bias current, it will be the opposite story. So your current will be basically smaller, and that's why in the future basically any kind of agreement and current we measure in the solar cell, I'm sorry, will be basically always talk about the forward bias current and not the reverse bias current. But now we're gonna see why this current is decreases if you have a reverse bias current. Basically, this is again, the first picture is in equilibrium when we don't have applied voltage. But here is if we change basically this pole, now it's this one, the negative, this one is positive. Then basically also the Fermi level, which is here without applied voltage constant through the junction, here will be also changed. But now it's changing basically in opposite direction. So now you shift now it's also your bottom of the conduction band shift, but deeper basically in this N-type region, and for the holes also. And now you can see, so the minority here basically of electrons in a P-type region is always the same, and there is no change in the story concerning the minority of the species. But now we can see basically that here in this one part, because here now we're gonna have built-in voltage plus applied voltage. So now this one basically gap, or this one part here will be much higher than here, because now we're gonna apply negative voltage, and here we're gonna have a smaller number, or how here is show basically that there is no available electrons, but basically the available electrons here are much smaller, so the current will be overall due to diffusion or due to the concentration gradient will be practically much smaller, and you're going to have dominant, basically, the drift field current from the minority of the species. That's the same story can be also expressed. So this is quite important. So if you applied basically the positive voltage, and we're gonna see when we show how it looked like the current voltage curve, basically your current will be increases. If you apply the negative voltage, and that we call reverse bias current, then basically you're gonna have a really small current, mostly only contribution from the drift field induced current. I'm sorry, I have a problem with changing the slides. Okay. So, and now the next slide, which we finish basically this story from the first part of this talk, it will be basically the ideal diode equation. And here basically we have applied electric field. So the story will be where the current is going from the P type to the N type. So we basically observe the forward bias current when we basically increase the current. And here we can we basically said when we have the forward bias current, then I'll just return on this slide that basically now we're going to have a much more electrons will be going to the positive discharge and much more holes going to the N-type region, and that this concentration of the holes will be next to the depletion zone, and also excess of electron concentration will be next to the depletion zone, just in opposite direction. And here basically if we represent how it looks like the concentration, so this is in a p-type region. Here we're going to have a lot higher concentration of the holes in a p-type region, but that's very small concentration of the electrons in the n-type region. These are basically minority of charge in the p-type region. And in opposite side, in n-type region, we're going to have a high concentration of electrons in the n-type region, and we're going to very small concentration of the holes in a p. Very small concentration of the holes in the n-type region. I'm sorry, and we also said basically, so the coordinates are the same. As for now, here you have a depletion zone, minus 6p, and this is basically xn. And we said if we have a forward bias current, then basically we have a lots of here much more electrons here than this minority here, and then electrons will be quite situated and concentrated next to this depletion zone. That's why we drawn here basically that the concentration, how we are close to the this depletion zone, it basically increases here. And also my minority species in the n-type region, which they are holes, also this concentration basically increases when you are next to the depletion zone or a space charge region. It doesn't matter. So basically, so the whole ideal diode equation, it's quite complicated. So that's why I'm gonna show you, I mean, for this time, just a couple last equation, and basically solving continue equation for minority carrier. Here is the number of, here is concentration of the electrons in the p-type region can be expressed like this. This will be applied voltage here, and here will be basically the coordinate x and xp. Ln will be basically diffusion length for electrons in p region, and that's diffusion length for electrons in the p-time region. Also, it's basically the distance. It's usually concerned only for minority species, and basically we represent the how much these electrons can move in the sample before they recombine with the. And here, for instance, we can also see that if we are, for instance, quite far away type region, so we are deep here in the p-type region, basically this one coordinate will be a large negative number. So this one exponent will be a large negative number, and this we're gonna get exponent of the large negative number, which will be 0, and then this one whole part is gone, and then you just have that the concentration of electrons as majority is just a minority concentration of basically in the area. And basically, if we are somewhere close to this age or this depletion zone, then basically your coordinate x will be minus xp. So this one will be 0, and exponent of 0 is basically 1. Applied voltage will be positive, and exponent of the positive number is larger than the 1, and then you're gonna have of this minority species, which basically increases next to this depletion zone. Completely the same explanation. It's that I guess I don't have to repeat it now. It's also for the whole. Now we also have applied voltage. Now just we're gonna have diffusion length for holes and region. And if we define this minority concentration, basically we can give finally the junction current. And the junction current for the electrons will be just charge times diffusion current. And this is because the charge is negative and diffusion is also negative, it will end up with a positive. Here you have basically the derivative, so that means that you have to integrate this equation, and then you end up here with the diffusion coefficient of the electrons, also diffusion length for electrons in p-type region, and here you have and the minority concentration, of course, and here you also gonna have the applied voltage. And for the holes, it will be completely the same, just here we're gonna have a minus because the charge of electron is positive, but here we have a negative diffusion coefficient and concentration gradient, and will be depends. Now will be just diffusion coefficient for the holes, and here will be diffusion length for holes in N region, and here we're gonna have, of course, applied voltage. So basically, if we want to write down on the easiest way, so the total basically junction current we can write down as a current from the electrons and current from the holes, and this will be expression GS, and here we're gonna have applied voltage. This GS we call reverse saturation bias current, and this will basically depends on many things, which will be basically the charge, then diffusion coefficient, minority of electrons, and also diffusion length. But for instance, if we basically represent how the G over the GS in a function of applied voltage, here basically you're gonna see, and we're gonna see in the next slide when we really show how the solar cell is working and how we measure the current voltage dependency. Here we can see basically that you have a really, really small current for the negative voltage, and then basically your current is just growing fast when you apply the positive voltage. So basically the equation, and now we go second part, which we call the light absorption and the photovoltaic effect, and where we can see basically how the solar cell is working. Before we see, we have to know something. Also, we have to define some absorption and that kind of stuff, but we're going step by step. Here, for instance, we have a p-n junction, space charge region, and for instance, you can so you can basically you use some photons of the light, or you lightning your p-type region, and when you're lighting your p-type region, electrons and holes are formed. So electrons are not feeling really well in a p-type region, and due to the basically drift field, he will go in the state with a lower energy and in the n-type region. It will be completely the same if you put the photons here in the n-type region. Again, electrons and holes are generated, but now the hole doesn't feel really well in the n-type region, and thanks to the built-in voltage, he goes to the junction and going to the lower energy state here. For now, basically, it's quite important that no matter are you illuminate the p-type region or illuminate the n-type region, your curve will always photo curve or light induced curve, it doesn't matter. So we'll always go from n-type region to the p-type region, and we're going to see. Before we go, we have to say something about the light absorption and, of course, the band gap of the material. So this is quite important, because if we, for instance, if we have a incident of light, which will, of course, depends on the wavelength. We said that basically the incident of light with some intensity penetrate to some matter to the some deepness here in this delta, basically x. So basically, if that incident of light will be absorbed by this matter of the thickness delta x, then basically your intensity will change, or the incident light intensity will be higher than intensity of the absorption through some matter. And usually in this situation, we basically make some assumption, and that is basically that the change in density due to absorption is proportional to the intensity that is there. And to write down in the form of the equation, we can basically write down that the derivative of the intensity will be proportional to some constant, then the light intensity, and then the thickness of the matter. This constant we call the linear absorption coefficient. And if we integrate this equation, basically we can find that the intensity after some penetrating some thickness, basically x, it will be equal to the incident light intensity times the exponent on minus linear absorption coefficient times the thickness of this matter. And if, for instance, now we wanted to show how it looked like this absorption for one of the semiconductor, and in this case, for instance, will be for gadolinium arsenide. Here we look what's happened with absorption in a function of the depth, the matter. And here we plotted for the different wavelength. Now we, of course, remind ourselves that the wavelength is it's oppositely proportional to the photon energy. This is how I see just the constant, Planck constant, and the speed of light. And here you can see basically that if you have a if you have a photon of the lower wavelength, then you will gonna have a higher energy of the photons. And the opposite, if you have a higher wavelength, you're gonna have a lower energy of the photons. And here you can see basically that here is exponential function, and this one basically the line, it's for the highest energy of the photons. And here we can see that the highest energy of the photons are absorbed the best. And then when you decrease the energy of your photon, he basically penetrates deeper and deeper in the matter until we basically come to some changes in the energy of a photon, where it's obviously that that photon is just won't be absorbed almost at all from the matter, and just going through there. And this is basically, now on the next slide, we're gonna see why is that. I just wanted to say basically that sometimes it would be logically, for instance, to think that if you have a higher energy of the photon, you expect that he basically go deeper or penetrate deeper in the matter. But basically here you can see that it's not like that. So the lowest energy photon penetrates deeper, and their absorption is lower than for the highest energy of photon. And this is because of the fact that the more energetic photons have the most processes available for the absorption of light. And that's why they strongly absorb basically. And here, for instance, if we represent how the linear absorption coefficient, depending on the wavelength and also on the photon energy, here we can see basically that the linear absorption coefficient decreases with decreasing of energy, and then in one moment when the energy of the photon is low enough, or the wavelength is enough high, then absorption is almost doesn't exist. So your photon is going to the matter almost without any kind of interaction. This is because the energy of the photon is reached basically the value which is below the band gap of this semiconductor. And the photons, which they have a smaller energy than the band gap of the material, cannot cannot create the carriers, and they cannot basically participate in working of the solar cell. So they are completely not useful. And that's why here basically is huge change, because here on the last wavelength, so the energy of the photon is so small, it's smaller than the band gap, is smaller than the 1.42 electron volt. So he just going through this matter without any kind of, it seems, interaction. So now it's interesting also to set something, because we something like the light absorption by a semiconductor. And here we have, okay, just an easy and familiar equation, and we can view light. We can also view light as particles flux of photons. And now because we define that we cannot use the photons, which they are smaller energy than the band gap. So that means that we have to use the photons of the higher energy. But we're gonna now to see what happens in the semiconductor also, what kind of processes also occur if we use the energy of the photon. And now, for instance, we're gonna use the blue photon with the smallest lambda of the wavelength and the highest energy, than the, for instance, green photon with a higher wavelength but the smaller energy of the photon, and also the red photon with the highest wavelength and the smallest energy of the photon. This is just I plotted to remind you from some of the previous lecture how it looked like the number density of the photon independence of the energy of the photon. For the green line, it's for the 1.5, IM 1.5, and here is just plotted also the dependency for the black spectra of the black body, observed almost on the 6,000 Kelvin, which quite well fitted with distribution of the photons. And now, for instance, here you can see basically that if we use the photons with the three different energy, for instance, the blue one photons, which will excite electrons from the valence band to the conduction band. Here in the valence band, we'll have the whole difference between the energy here and here, electrons and holes, exactly the same as the energy of this photon, and it will be same story. And for the green photons, just here is smaller energy. Also, this one difference here between energy level of the holes and the electrons will be also the same as the photon energy, and also for the red one. But the problem here, when you use basically the more energetic photons, basically that the hole and electrons basically quickly relax and ages. So that means that the electron here will be go in a state with a lower energy here at the bottom of the conduction band, and also hole here in the valence band go in the position of the lower energy and the top of the valence band. And here, and then in the death process of relaxation, basically they release the heat. Heat is not good for the solar cell, and they can influence efficiency of the solar cell, and I mean on the bad way. That's why it's not good. And here, for instance, we can see that if you use the blue energy of the photon with the highest energy, so the process will be also the same relaxation, will end up no matter what kind of energy of the photon you use. Just here, when you use the highest energy of the photons, he will basically release the biggest heat here. So that means basically that must be, so it's not always good. So just to say that we can, then we need to use the highest energy of the photon. There will be always some optimum band gap, basically, that we can abstract the maximum power. And we discussed about this some of the next slide. But it's also important to say here now we can look at the light absorption in a function of the fraction of absorbed. This can be also expressed in 1 minus ratio of intensity. I mean, it's a 1 minus because the value of the absorption maximum is 1. And this also can be expressed as 1 minus exponent on the absorption coefficient times basically the thickness. And if we look how it looks like dependency of the fraction of absorbed in a function of the depth here, for the three different semiconductors, which is silicon, gadolinium arsenide, and also germanium, for a three different wavelength. Here, for instance, you can see basically that the absorption for the silicon is the smallest compared to the other semiconductor. So basically, here the light penetrates for all three different wavelengths the most compared to the other semiconductors. So if we look how the absorption coefficient is changing, for instance, for germanium, so here you can see that absorption coefficient decreasing, and then suddenly when he reaches some wavelength or the energy of the photon, which is below the band gap, you have a drastic drastic fall. It's completely the same for germanium, just this drop will be on the highest wavelength or the smallest energy of the photon. If you look the silicon, so here you can see that this one changes are much more gradually, and there is no such a sudden drop. And this is basically because of that, because the germanium and gadolinium arsenide are direct gap. And the silicon, and I mean, when I said silicon, I mean crystalline silicon, is basically indirect gap. And there is basically a difference between them. And now we're going to say what kind of difference. So if we basically look dependency, which we have in the first lecture, when we talk about the free electron energy, if we look what is happening with electron energy compared to the electron wave number or the momentum, how we call this K. So we see here that the free electron energy is proportional to the momentum on square. And if we represent basically for the conduction band here, we're gonna have some parabola basically with the minimum, and this is the minimum of the conduction band, and on some values of momentum. And for the valence band, we're gonna get completely the same behavior, just this parabola will be opposite. I will not go in the physics of this, but I can tell you that it is because electrons sometimes can behave like they have a negative effective mass, and as they behave, as they have a negative effective mass, they can be also concerned as a whole. That's why here this one curve will be in opposite direction. But anyway, the bottom of the conduction band and the top of the valence band, we're gonna have the same momentum here. So that when we use the photons, so basically the electron from the valence band can be quite easy go in available electronic state in the conduction band. And here for the silicon, the story is quite different, because here the bottom of the conduction band will be on the different momentum here than the top of the valence band. So basically, when you excite the electron from the valence band to the higher, there is no, so he will come to this one position where there is no available electronic, empty electronic energy where he can be. So because the here available electronic energy are in the different momentum. And that's why we said that we use basically in that cases for the indirect gap, we use the phonon assistance. Phonon is a basically the quantum of the lattice vibration, because every lattice basically vibrate to some frequency. So the phonon will basically bring some frequency and momentum, and he will basically allow the electron to change momentum and to go in the available electronic level in the conduction band. That's why, because of all this much complicated process, that's why we have here gradually changing absorption coefficient, and not here directly as we have in a case of germanium, or in a case of, in a case of gadolinium arsenide, or in a case of germanium. Now we can also say that basically it's important here to say that this is the same semiconductor, but a different modification can have a direct and indirect gap. For instance, crystalline silicon, it's have indirect gap. But that's why the amorphous silicon that we also use in a solar cell have direct gap. And always in semiconductor will be basically opposite. For instance, antimony sulfide that I use in a solar cell application, so their crystalline their crystalline shape is direct gap, it's opposite than the silicon, but amorphous shape is indirect gap, and that will be always in semiconductor. So if your crystalline shape is direct, then amorphous will be indirect and opposite. So, but let me now return in the case of the silicon. So crystalline silicon, which they have an undirect gap. So actually, we see that the undirect gap means basically lower absorption. And what that means in the sense of application of this crystalline silicon in a solar cell. So basically that means that if you want to use the crystalline silicon in solar cell, you need to have really thick layer of the crystalline silicon, because basically your photons will penetrate really quite deep in this layer or this film of the crystalline silicon. And also your crystal lattice of the silicon should be really make perfectly and not have some defect, because if they have some defect, then also we're gonna have a nice a recombination process between electrons and holes will prevail, and that's also bad influence on the efficiency of the solar cell. And now we can also say something about the solar photocurrent. And we also use one of the graphic we explained in one of the previous lecture, and now on the one in one of the previous slide. And here, if we basically again look the same distribution, so the number density of electrons in the function of the of the photons in a function of the energy of the photons. Here we can see, so for the IM 1.5, this is the green line, and here we can see how it looks like distribution for the black body observed around 6,000 Kelvin. And now, for instance, if we want to find the number of the photons, some specific energy, which is the higher than the band gap of the material that you want to use in your solar cell, we can basically integrate this number density of the photons. And here basically we presented for the crystalline silicon, which band gap is around 1.1, and where we're going to integrate for 1.1 to infinity. And here you're going to get by integration this dotted line here, and the number of the photons, they have an energy higher than 1.1, higher than the band gap of the silicon, will be basically you get here on the this line, and they're going to give you the number of the photons with the highest energy than the energy of the band gap, which you can use basically in the charge generation in the solar cell. So basically we can express this photon-induced current as the cell area. This is for the whole cell, for the current times the charge, and then we integrate the number of the photons from the band gap of the material that we use in a solar cell to the infinity, and here we're going to get by integration the number of the photons. So it seems when we explain like this, that basically the lower the band gap energy, we're going to get the greater photocurrent. So now we can say basically, so okay, now we can take material somewhere here in the maximum of this curve, so below the 1, and then we are going to have the highest definitely number of the photons which you can use in a solar cell application. But the situation is not basically so much easy, because the energy per carrier basically drops with decreasing the band gap. And if we ask ourselves, can we find the band gap basically for maximum power? Yes, because that is basically one interplay to find the suitable gap that you can find the maximum power. And that band gap of the material will be approximately between 1.1 and 1.4. And now we're going to see the EV curve conventions when we have a p-n junction. And here we're going to see basically what is happening. So we have a p-type region again, an N-type region, we're going to have depletion zone, and we're going to have, because of a depletion zone, we're going to have a built-in electric field. And now if we apply the here basically we get the forward bias current, and forward bias current, we're going to have this direction. We're going to go from positive to negative. That will be basically the way of the forward bias current. And if you measure how it looked like the current in a function of the voltage for this forward bias current, you're going to get this dotted line here. So if you have a negative voltage, if you remember now the first lecture, if you have a negative voltage, you're going to get a small current. And then for the positive voltage, you get a positive current, you're just current going up. And this is why we call basically the positive current when they go from the positive to the negative way. But for solar cell, much more common to measure positive current flowing, but from positive to negative side across the power supply. So here basically we have some resistor, which is, we can say is some power load in our cases. But that means if we measure the current, which they going from positive to negative pole, but across the power load, that means that this current we have an opposite direction than the forward bias current. And if we measure basically how it look like the current in the function of the voltage, we're going to get now the small current for the negative voltage. And now for the positive voltage, we're going to get basically the high but negative current because it's in opposite direction. So this one basically curves will be completely the same, just this one is positive current and we're going up, and this one is basically negative current, and that's why we'll down, and we're going to give even a negative current for the positive voltage. Now, we will basically induce the light-induced current. And this light-induced current, remember, we said basically that going from the N-type region to the P-type region. So it's going from the negative to positive, and then it's going in this direction, and then of course it's going to the positive, from positive to negative across this power supply or load. So basically the direction of the light induced current will be opposite than the forward bias current. And if we measure how it looked like the current in the function of the voltage, we're going to get this curve. For this measurement, basically, we have a two. Here is where we can abstract the maximum current, and that maximum current we're gonna get for the zero voltage. So when here is a zero voltage, we're gonna get the maximum current, and that current we're gonna call circuit current. The second, so how we basically increase our voltage, increase the voltage here is a positive voltage because we increase, then in one point, when you reach enough high voltage, your current will drop, and this one point, when basically the current is zero, we can get the maximum voltage of the solar cell. And this one point we call circuit voltage. And in the next slide and the last slide, we're going to see how we can express these 2 points. And these 2 points basically are quite important because they will participate in the efficiency, in the expression for the efficiency of the solar cell. So here we can say basically that the whole current we can write down on the way that basically will be light induced current minus forward bias current, because the forward bias current have the opposite direction than the light induced current. And this can be basically expressed as a light induced current minus forward bias current is just given by the ideal diode equation. And if you remember from at the end of the first lecture, basically this one is AS will be reverse saturated bias current and will depend on the minority of the species, charged species, and also, of course, from the voltage. And here we can see basically, here red one, if we measure how it looks like the current voltage dependencies, this one just red point is just point that you get basically by changing the voltage and measuring the curve, and then you just fitted, yeah, how it looked like basically your dependency depending on this measure point. And here basically we said that we have a short circuit current, and this is the maximum value of the current we can have for the zero voltage. If you look, for instance, this equation, if we put that the voltage here is zero, that we can calculate the maximum current, then we're going to get exponent of zero, which is 1. 1 minus 1 is 0. So basically, you're going to get that your short circuit current, so maximum current, this one point here, is just equal to the light or photon induced current. This is the situation where we don't have a resistance, we have a voltage, and when we don't have a voltage, we also don't have a no forward bias current. And for the next point we want to get, and this is the maximum voltage, we're going to measure when the basically current is 0. And if the whole current is 0, then one whole expression can be basically 0. And then from here you can abstract how much is this voltage. Here we can see basically that the circuit voltage depends on light induced current divided by reverse saturation bias current, which depends basically quite well on the minority carrier in the so that's basically electrons in the p-type region and the whole n-type region. So basically, I will finish for today my talk.
Well, thank you, Ivana. This was a great talk, and I appreciate that you talked basically for an hour and a half, without stopping. Usually, when we teach here, we make a break, in the half. Like our classes run like 110 minutes, but with a break.
Yeah. We have a lot of things, to explain and to show, and basically, when you start this kind of explanation, it's better to continue. I think somehow that the people is easier to understand if you continue and if you from once connect some.
I agree. So for interest of time, I suggest we go through a couple of questions if there are any questions from your group or from Tyler or anybody else.
I don't know if some have.
Well, I can ask a question that is, about mobility.
This was too much. Yeah, I know that usually, when you teach this introduction in photovoltaics and physics, it's usually complicated, because of this formula. But basically, you have to just follow the basic things. But it's quite difficult to explain anything if you really don't use the formula and if you don't come a little bit deeper in physics to explain, for instance, how something is changed. And
yeah, I agree. I think there is always theory behind the experiments that pretty much all of us do.
Yeah.
So background information is important. So my question is about mobility of electrons and holes. At one of the first few slides, you mentioned about mobility in different materials.
You mean for the different semiconductors I just
for
mentioned,
different semiconductors, yeah. And trying to relate that to mobility of ions in gases. So my question is basically, Is there a formula that describes, how mobility changes, depending on the type of semiconductor? I assume with
just to find, this, where is expression of modality? I'm sorry. But basically, I mean, I can answer and doubt this, but not so much. Yeah, here is in the beginning, basically, the mobility. So I said here, you can see basically that is mobility of the electrons and holes is changing depending on the semiconductors. And usually the mobility of electrons and holes are also related with their effective masses.
So
Why? That's why, for instance, for usually the mobility of electrons is much higher than the mobility of the holes, because the effective masses of electrons for the most semiconductors are quite basically higher than the mobility of the holes. And the effective masses for the most semiconductor used in a solar cell are more or less similar. I don't see that some specific changes, except in the case of antimony sulfide, which I'm doing, but I will show this, and this basically their difference between the effective masses of electrons and holes are more drastically. And just because that drastical difference in the mobility, we also explain how the just a simple photoelectrochemical cell is working. So by mobility of electrons and holes, you can even explain.
So it basically depends on the reduced mass, what mass of, as you said, electrons and proton, and also depends on the mass of the atoms that are found in those semiconductors.
Yes.
And I assume it's inversely proportional to temperature, or square root of temperature. So the
Here, mobility is the function of the temperature, yes, and doping, of course. Doping. Yeah.
Sounds good. Yeah, like I try to relate to mobility of ions and gases, and there is an equation that describes how mobility depends on those factors. So it appears to be quite similar to what's going on in semiconductors.
Yes, the mobility is quite important, for the, for the photovoltaics, especially I'm telling you because, for instance, for the antimony sulfide, which we are doing, so their effective masses are not of electrons and holes are quite drastically different than the most semiconductors that the people use so far. So basically, you have even a much higher difference between effective masses of electrons and holes, and basically by this huge difference, you can also explain how your photoelectrochemical solar cell is working, because due to the different completely movements of the electrons and the holes, due to the concentration gradient and also the Drake field.
Sounds good. Any other question or comment?
Any other question?
Well,
no, this was too much.
Yeah, I think it's getting late in Belgrade, I understand, and here, just coming.
Yeah, it's almost.
Yeah. Well, if not, I'll stop. I will stop recording, and probably tomorrow or during weekend, I will download so that you can post on
okay
on YouTube.
Okay.
Yeah.
Okay, then I can disconnect the presentation.
So figure out how to split this.